Okay, I'm start streaming. Good morning, everyone. Today I'm going to give the lecture. Can all hear? Test. Testing. Okay. So okay, good. So I'm going to carry on where we stopped on Tuesday. In the Tuesday lecture, we have covered about the time complexity. We cover about the time complexity. I have introduced you a few typical structure in your algorithm and how do you analyze the time complexity on this structure. So typically all these standard primitive operation is not really, each of them, the operation, how much time you take is not what we concern. We more interest about how the problem size influence affect the number of primitive operation. So for example, if you have a repetition structure, that means the for loop, while loop. Of course, if your problem size increase, the number of iteration probably will also increase. The number of iteration increase, that will affect the number of primitive operation a lot, the number of it. So that is what we concern. The next thing we need to consider when we analyze the time complexity of an algorithm is if you have some if-else statement. In that situation, the if-else statement or switch case, that means not all the primitive operation will be executed. It depends on your input, all the scenario you need to consider. Yeah, because certain case you may execute the true cases. Certain scenario you may run the false cases. So we need to consider all the scenario and trying to understand the time complexity of an algorithm. That means normally we interest about the best case, worst case, and on average, all the possible scenario, on average, the time complexity. These are three basics, the typical scenario we would like to know before we decide whether we should choose this particular algorithm as our final solution. Another one is the recursive function. Recursive function is also same thing. You trying to count the number of primitive operation, but there's a recursive call. So you need to know the number of recursive call. And then in each number of recursive call, you have done how many primitive operation. And that is what we cover in the Tuesday lecture. So I have give you this example. So I don't want to go through it again in the Tuesday lecture. So we need to consider best case, worst case. Best case, why is the best case, worst case, and average case? It's just like you want to have a picture, the overall, all the possible scenario. Yeah, and how is the perform best case, worst case. Yeah, that means the shortest time you need to run this algorithm and the longest time you need to run this algorithm. These are the things we want to know before we choose when we analyze the algorithm. So sometimes it can be very complicated, and then when you analyze all this repetition structure and recursive function, you will realize that every time you need to count the number of recursive call, and in each recursive call you need to do how many primitive operation, and you're trying to sum it up. So you will find that actually a lot of time in mathematics, the knowledge you need to have is the series, because you can find that this example is relatively simple. Every time you just have one, always you have only one primitive operation. Or in this question, I'm only considered particular primitive operation, which is trying to the number of this comparison. So in that situation, not surprising that every recursive call you only do one. But you will find that in many situations, the number of primitive operation may not be consistent. That means every call, every iteration, it may not be always this particular number of operation. So sometimes maybe 1, 2, 3, 4, 5. Sometimes maybe first iteration is 1, second iteration you need to run 2 recursive call, and then 2 operation, then third iteration maybe 4, maybe after that is 8, 16, 32. Yeah, just like this example. Yeah, you will find that every recursive, every recursive call, you have different number of primitive operation. Then you have different number of recursive call. Yeah, you do in this example is I did 2 recursive call in each function call. So end out that the result is exponential increase. And the relationship, you will find that this is a geometric series. So you'll find that you need to use, a lot of time you need to use some series to solve the problem, to find the time complexity. So this one I have highlighted on Tuesday. Yeah, you will become an exponential function. So these are, which I have shown you in the notes, the derivation. Yeah, here we focus on how to use them. Then one of the example is this one. For example, I have 3 for loop here, nested loop. Inside is trying to do the multiplication. That means this one is like if you have a vector A, I have vector A, and I have another vector or array, 2D array, and 1D array, sorry, 1D array. So in my output is M. The first element is trying to run a nested loop. That means it's the first element times the first element. In the second one, the second element of the output M actually is this one times this one plus this one times this one, and then plus the second element of A times the first element times the second element. Let's say this is my algorithm I need to do. So what is the time complexity of this particular algorithm? You will find that in the first run, you only do one primitive operation. You do one multiplication. Then you only do this operation once. But in the second outer loop, second iteration of the outer loop, then you need to run 4 times. This one times this one, this one times this one, 2 times, 3 times, 4 times. Then after that, you got 3 elements and 3 elements. Then to multiply each other, that means you need to do 9 times, and so on and so forth. So should be first time got 1 square, second time got 2 square, third time got 3 square, and so on and so forth. So total number of primitive operation is 1 square plus 2 square plus 3 square plus 4 square to n square. So what is the summation of this series? That is the time complexity of this algorithm. And then from the previous notes, you can read the derivation. Here I just simply apply this formula. Then I will find that it's n times n plus 1 times 2n plus 1 over 6. In short, not surprising, there are 3 for loop. Then they are linearly decrease, linearly decrease, linearly increase. That means they are linearly. Then implied that this one, that is what today we are going to cover. You will find that actually you do all this calculation, in the end you find that conclusion is that actually this thing is in n cube. We are concerned is like this is an n cube. Although there's an n square, there are I think this one, if you expand it out, it should be 2n cube if you want to have a more precise result. 2n cubed plus here got 1n, 2n, so 3n squared. Then plus this one got 1, and after that this one times this one, this one times this one, then this one times this one is n. Should be 2n cubed plus 3n squared plus n over 6. But actually this one, you'll find that this particular term will dominate. Behind you got n squared and n, compared to n cubed, this one will grow much faster than these two terms. So overall, you will find that this is the n cubed algorithm. It's a qubit times complexity. So actually, when we analyze the time complexity, that's why I said we're not so particular about how much time you need to take to execute one particular primitive operation. Or we also not so particular with like all this n and 3n. If I have one term, my time complexity, there's an n cube. Actually, this and this is not so important. Yeah. Why am I say so? Just give you an example. Let's say I have a few algorithms here. I have 6 algorithms here. Their operation is, the first one, you need to take 13n operation. Then the second one, you need to take 13n log 2n operation. Then the third algorithm is 13n squared. Then the fourth one is 130n squared. And the fifth one is 13n squared, similar to the third one, plus additional 100 operation, extra operation, constant. And then the last one is the exponential function, which is 2 power to n. Let's say each operation, I need to take 1 microsecond. It's a very slow computer. Then let's say my problem size. Now first I try when n equal to 10, 100, this how many? 10 power to 4, which is 10,000, and then to 1 million. Then in this situation, yeah, what is the difference? In the first algorithm, let's say 1 microsecond, you will find that it takes 0.0013 seconds to complete. You increase 10 times, you increase 10 times, 100 times. Yeah, this is a linear function, so they also increase it linearly. Then if you look at different algorithm, the n equal to 10, okay, this is less than 1 second. This one also about the same, 0.00043, 1343, about the same. And then n squared is a little bit slower, but it's also 0.0013, still fine. This one is 0.13. This one is almost the same as the third algorithm. These two are about the same. Just because of this 100 extra operation is not significant. 2 power to n algorithm, initially also not a lot, 0.01. Yeah, even slower than the fourth one. This one is the slower, is the slowest one. This one still a little bit faster than this initially. But when I increase the problem size, you will find that if you compare the first algorithm and second algorithm, this one, when you have 1 million, of your problem size is 1 million, you already need to take nearly 5 minutes to do it. But this one, 13 seconds can complete. If you further move to n squared, you will find that it takes days. Yeah, the third one and the fifth one is about the same. When you increase to a large number, your problem size is a large number, this one is negligible. You can ignore. It's nothing. This one already 22 minutes plus that 0. few seconds is, you can basically can ignore it. No too big difference. Yeah. Then 130 n squared. Actually, if you notice these two, their growth is about the same rate. When you go to minutes, this one is in hour. When you are in days, of course this one still 10 times 10 times lower than the algorithm 3 and algorithm 5. But you will find that compared to 1 and 2, the goal rate between this one and this one, you can see that it's bigger difference. This one is still in second. This one already in day. Yeah, the worst is the last one. The last one basically, you only increase 10 times. You already need to take, I don't know how many years, 10 trillions, I don't know how many trillion years you need to wait. Basically, you have no chance to see the result. So that is the when we analyze the time complexity, why we need to focus on, we only focus on the nominate term. Yeah, n square is n square or n square or exponential or linear logarithmic or n. You will find that whether it's the 13n square or 130n square is not that critical. If you look at the diagram in the next slide here, you will find that if you have a logarithmic, if your time complexity is a logarithmic, it will grow very slow. As your n increase, my problem side n increase 10 times. This is a logarithmic diagram. So this is the chart. You increase 10 times, 10 times, 10 times, 10 times. But this logarithmic function grow very slow compared to linear function. And then among these algorithm, let's say all this is the time complexity of an algorithm. You will find that the worst one is this n factorial. Because n factorial, initially n factorial, the time complexity is not that bad. It's 1 times 2 times 3. But slowly you are multiplied a bigger and bigger number. So you will find that you will grow, you shoot up very fast. Less than 10 already here. Less than 10. Beyond 10, you can expect that you will go, don't know where is it. Then the next one is the exponential function, 2 power to n. It grows also quite fast. Initially, it's lower. It's much implied that this initially when you have less than 1, 2, 3, 4, less than 4, about less than 4. Basically these two algorithm is the faster one. But after your n increase beyond 4, 10, 100, 1000, these two algorithm, the time complexity, actually is quite scary. The computational time is very scary number. Then if you compare from here, you also can find out that the logarithmic is the slowest one. Linear one is okay. Then if you go to compare just now the 13n square and 13n square plus 10, initially there are some different because you need to run additional 100 additional operation. It look like this one is need to take more times, but as the times goes, your problem size getting more and more. Your problem size increase. Actually, that 100 additional operation is nothing. Compare your n increase. Your n grow 10 times. That 100 is basically you can ignore. So normally we will ignore all this term. We only look at the highest power term, the polynomial term. So if there's just now the earlier example, we only look at the n cube. That particular term is more important because as my n increase, this particular term will grow very fast. You got additional n square term or n, basically you can ignore. So and then compare the 13n square and 130n square. You can look at this one and this one. Basically, of course, this 130n square always grow faster than the 13n square. But you can find that this, after your n grow higher and higher, is almost parallel. Yeah, the way they grow is in the growth rate. We are talking about the growth rate is about the same. Yeah, they're almost parallel. Just like one guy a little bit faster than the other one. But compared to exponential, yeah, the growth rate are different. One is go out in this way, the other one is just grow in this manner. So this is come to how do we represent the time complexity. Yeah, today I have different algorithm. Yeah, I think someone just now asking that any example of algorithm that has the logarithmic times. Yes, binary search is one. Yeah, we will cover it later. Yeah. And normally you will find that in many algorithms, as long as you're trying to I would say you will find those algorithms like decrease and conquer strategy. Likely is the logarithmic. Because every time you have a problem, your problem size is n. You don't really use all of them. You're trying to filter out half of them, half of them, half of them, half of them. So that can reduce your search time. That is the binary search we will cover in the week 5, week 6, probably in week 5 or week 6. Yeah. So that's logarithmic. Later I will mention those algorithms. You'll find that how do I have an algorithm? Actually, yes, I don't really need to get very precise number of primitive operation. I just need to roughly know it is a linear function, is a exponential function, is a logarithmic function. Their relationship. How do I represent this time complexity? I'm only interested about their order of growth, their growth rate. So that's people come out this asymptotic notation. So here I'm going to introduce you the big O, big omega, and big theta. Yeah, the typical asymptotic notation. You may heard normally online you can always see people talk about big O. Yeah, when they discuss about certain algorithm. So the asymptotic notation used for describing the order of growth. So very important is order of growth of a given function. So typically you can classify this into 3 types. Yeah, so take notes. When we talking about this is this function is in big OG. What does it mean? Is big OG is a set of functions that grow at lower or same rate as G. So it's a set of function. Take note, it's a set of function. What does this thing means? Let's say example, my G is n squared. You can refer just now the chart. If my G is n squared, yeah, what are the possible function f? Any idea? N is 1. Linear function, yes. Any idea? Any function? If G is n squared and f set of a function that grow at lower or same rate, n log n, linear logarithmic is lower than n squared. Yeah, this is a good example. N log n actually is lower than n squared. Then, yeah, n squared minus 1 grow at lower or same. They are the same rate. So n squared minus 1, n squared minus 2, n squared plus 1, n squared whatever. Even in this category, n squared plus n is also same growth rate. Because basically you can ignore the constant, you also can ignore all the linear term. Because the quadratic term will dominate the whole growth rate. Yeah, whether it's log 2, base 2, base 10. Yeah, I think this conversion you need to know. If it's a base 2n, I convert it to base 10. Over, yeah, these two are equal. So whether it's base 2, base 10, no different because this is just a constant. Just multiply some constant. So basically, when we talking about logarithmic, base 2, base 10, base 5, base 7, whatever, or natural log, actually they are in the same growth rate. They are in the same growth rate because I can easily change the base and just multiply a constant. So if you put out the chart, the growth rate are about the same among different base. So all this we can consider they are in big OG if my G is n squared, because big OG is a set of function. Then for big omega is a set of function that grow at higher or same rate. So what are the higher one? So this is n squared, implied that the earlier example, the n cube one, is higher growth rate. Anything else? Exponential is one. Factorial is another one. Yeah, a lot. I can easily, or e power to n. Also, of course, n, all the polynomial term n power, 2 power to n, 2 power to n is 1, is higher. Or same, n squared minus 1. Just now earlier we mentioned n squared minus 1. It also, under this, is also in big omega g, because same, higher or same. So if you have the same growth rate, you can say that it's also in big omega g. Then what is big theta g? That's when they only considered those growth rate at the same rate. So n squared minus 1, in this example, n squared, n squared minus 1, n squared plus n, or n, probably, I even can say n plus 1, n plus 1 square. N plus 1 square. Also in the growth rate, also in the big theta g. They are in the same growth rate. So 10 power to, yes. You just multiply another constant, some constant in front, n square. They are the same. You 10 plus, more complicated, it's like plus 1 square, then plus, since it's n square, right? I just add another logarithmic. Whatever you end it, because the nominate term is n squared. The rest behind all this small lower growth rate you can ignore. So all this considered, this function, all these functions are in big theta g. You can think out a lot of similar function here and there. So take notes, is a set of function. So that's why proper notation, I should set f is in big theta g. But in computer science, this is the definition in computer science. When I talk about big O notation, the definition, the formal definition in computer science, I have to emphasize in computer science. Let f and g are two functions such that, these two functions, is fn is said to be in OGN, and we denote this notation. And if fn is bounded above by some constant multiple of gn for all large n, then that is the definition. So for every positive constant c and n naught such that fn is less than some constant times gn, then you can set that fn is in OGN. So in computer science, instead of use this notation, a lot of time you will find that they will use equals. They will simply set fn. You may see a lot of time people just simply set equal to OGN in computer science. But by definition, actually, fn is supposed to set in OGN. But in computer science, we can accept that you just simply write this way. Okay, what is this definition? Okay, this is the formal definition in mathematics, people doing so. What does it mean? That means as long as I can find a number and not, and any problem size bigger than n naught, and I can find that there's a constant, any number. You as long as you can find one number, yeah, times gn, and this particular cgn, yeah, bounded the fn above. Yeah, so that means fn is bounded above by this particular cgn function. Then you can conclude that fn is in OGN. In other words, that means your gn, your cgn, that means after certain point, it grow a lot faster than the fn. Fn have no way to catch up. In that situation, you can set fn is in OGN. So maybe give you an example. So let's say I have a function 4n plus 3. My fn is, there's some time complexity, which is 4n plus 3. My gn is n. Are they the same? Are they in, yeah, does fn is in OGN? Well, I can easily find that if my c equal to 5, in fact, you can find any number. As long as I can find one number, it's already fulfill this criteria, then fulfill the definition, I already can make the conclusion. And n naught is equal to 3. Yeah, you need this fulfill fn plus 3 less than 5n for every n greater or equal to 3. In that case, basically I can conclude that fn is equal to OGN. Take note that someone asking, does big O represent the worst case scenario for big theta? It's not correct. Yeah. Now is notation. Big O is a notation. It's just a notation. It's just how I represent this particular. Yeah. Instead of every time you tell people that, oh, the time complexity of this algorithm is 4n plus 3. Basically, people actually not interested about it. You just simply tell people that this algorithm is in big OGN. It's good enough. I know, or big ON. It is what I'm concerned is like whether it is a linear or not. I'm not really bothered about is 4n or plus 3. So that is why we use the big O notation. Yeah, it's nothing related to worst case scenario or what. Yeah, basically it's just a kind of a representation. Instead of represent your time complexity. Of course, this is, if you have a algorithm, the time complexity is 4n plus 3. Well, you can say that, yeah, the time complexity is a function of 4n plus 3. It's fine. But actually, people just want to know whether it's linear or not linear. So that's why we come out this notation, big O, big omega, and big theta. So this is a very important concept you need to know. Yeah, why you need to write your time complexity in this particular notation. So that is the definition. So from here, yeah, as long as I fulfill this definition, I can simply set that, yeah, fn is equal to OGN. That means this particular time complexity is ON. Okay. So similarly, this one, yeah, another example here. Yeah, this is another example to answer your question. So if same thing, I have another same function, same time complexity, 4n plus 3. And then is it in n cube? Is it in n cube? Okay, same thing. I follow the definition here. As long as I can find c equal to 1 and not equal to 3, then, yeah, 4n plus 3, yeah, is less than n cube. Always less than n cube when n greater or equal to 3, right? In that case, yeah, because it's bounded, so it's always less than, yeah. Then I can conclude that 4n plus 3 is in big O n cube. Because this one, the growth rate definitely is lower than n cube. Yeah, intuitive, you don't really need to prove. Yeah, but you want to proper mathematician, I think you should proper follow the definition and prove that, yeah, if it fulfill this definition, yes, so I can make this conclusion. But intuitive, you look at it, one is a linear function, one is a cubic function. You already know that the linear function definitely have a lower growth rate than the n cube function. But this is the proper definition. You just follow the definition to prove and make the conclusion. Okay, so here I can conclude that 4n plus 3 is in all n cube. In other words, I also can set that if fn is equal to all gn, then we can set that gn is asymptotic upper bound of fn. Yeah, we can set so. Gn is asymptotic upper bound of fn. Yeah, it's upper bound of fn. It can be same growth rate or Gn have higher growth rate if you're using the big O notation. This is one definition. Another definition you also can use is trying to take the limit of fn over gn. If fn over gn, you take the limit and go to infinity, the result is less than infinity, implied that gn should be grow at the same rate or grow faster than fn, so that this ratio will give you a less than infinity. If you go to infinity, that means fn grow faster, right? So I also can use this particular alternative definition for big O notation. For example, this is, you can try the same example we showed earlier. If you take the limit 4n plus 3 over n, actually they give you 4, so which is less than infinity, then I can make the conclusion easily. Another one is 4n plus 3, and then this is n cubed, you take the limit 4n plus 3n over n cubed, you take the limit is 0. Not surprising, because this one grow faster, so the whole term, this part definitely will go faster than this one. Eventually you will get equal to, when n go to infinity, you will get 0. I hope you still know how to take the limit. So I skip the derivation here. Yeah. So fn will be in all gn. So fn plus 3 will be in all n cubed. One of the question, possible to have a periodic function if your time complexity that is trying to count the number of primitive operation. As your problem size increase, will it be sometime high, sometime low, sometime high, sometime low? Yeah, can you think out any algorithm? Can be sometime a while is linear, a while is cubic, a while is linear, a while is cubic, is a periodic. Even so, it can, maybe there is something like that, but then that will like just like what we did in the, we need to consider best case, worst case, and average case. So when we consider particular case, then unlikely it is a periodic function. So I would say that when we do the time complexity, the notation, so it should not be a periodic function. Normally it may not be always linear. Sometimes it's very hard to say it is linear or not linear. Yeah, why we have the big O notation? I think another student asking, what is the point of big O? Because you have this problem. Sometimes you have an algorithm. It may not be always linear. It may not be always n cubed. So in the end, you only can tell people that yeah, it cannot be worse than linear. So I only can tell you the time complexity of this algorithm is in big O n. Yeah, the time complexity basically is bounded above by this particular linear function. Yeah, like I said, you only have the you need to consider best case, worst case, and average case. So in the end, on average case, it cannot be periodic. You take the average one. Okay, so another way to represent your time complexity, another notation to represent your time complexity is big omega notation. So this one is the other way around. So same thing, the proper definition, yeah, you have two functions. Then if we set fn is set to be in big omega gn, denoted fn in big omega gn. Then if f is bounded below by some constant multiple of gn for large n, yeah, fn is bounded below, That means there's another function cgn, as you can see in this diagram. There's a cgn which is below the fn. Then basically you can conclude that fn is in big omega gn. Same thing, I also can use the another alternate definition, which is trying to take the ratio. As long as this ratio, I take the limit, is greater than 0, implied that fn is grow at the same rate or higher than gn. Then I can conclude that fn is in big omega gn. Same example, fn plus 3, phi n, both are linear function. Definitely you can find a c and n naught to conclude that 4n plus 3 is always greater or equal to 1/5 times phi n for all n greater or equal to 0. So in that case, you can conclude that fn is equal to big omega gn. And we can also set this is gn is asymptotic lower bound of fn. Similarly, for another one, this is the tightest bound. That's when you not only need to bounded, fn is need to be bounded above and below. It's bounded both above and below by some constant, two constants. So you need two constants, C1gn, C2gn. Or you can use this alternate, same thing. That's mean they have the, in short, more intuitive way, I think is like fn over gn, they have the same growth rate. As my earlier slide show you, you need to have about the same growth rate. That means both must be linear or both must be quadratic. So if you take the ratio and then take the limit, it should give you a constant number. Must be some number less than infinity but greater than 0. In that case, you can conclude that fn is in big omega, big theta gn. And we can set that fn is equal to big theta gn. That means gn is asymptotic tight bound of fn. So what is the definition of big theta limit? What is the definition? The definition is here. Yeah, fn over gn, take the limit equal to some constant. And this constant must be greater than 0 and less than infinity. Okay, so summarize. Yeah, if you have a function, if you're trying to take the limit, if you have a fn and gn, you're trying to take the limit. Yeah. Basically, you can conclude that fn over gn you can conclude that Fn over Gn. So n go to infinity. So if this ratio is 0, if this ratio Fn over Gn is 0, which means the Gn grow faster, right? So implied that Fn, you only can conclude that Fn is in big O Gn. If this particular ratio they give you is some constant number, which is between 0 and infinity, greater than 0, less than infinity, that means this one, you not only can set they are in the same, because they have the same growth rate, so definitely you can conclude that Fn is in big theta Gn. Since it's big theta Gn, that means that definitely also big omega Gn, also in big O Gn. If the ratio is go to infinity, then you only can conclude that Fn is in big omega Gn. Yeah. So how does? So you definitely can find. That's when you, if it's a, I guess you are talking about the big theta. If it's a big theta, that means I have a function f. I always can find one C1gn and another function C2gn, and they bounded above and bounded below. Yeah, Fn is bounded above by this particular function, and Fn is bounded below by this another C2gn. In short, actually, Fn and Gn, if you can make this conclusion, they must be in the same growth rate. So you always just multiply, just find some multiplier, multiply some number, you will be bounded, that particular function will bounded above. If you multiply some small number, then you are bounded below. So you always is a tighter bound. And why do we need these three notation? Okay, so that is important. So today you think about it, if I have an algorithm, and okay, let's say like earlier what you have learned, like repetition structure, you run number of iteration, always fixed, always that particular, it's always linear. Then probably when you make the conclusion, you want to give a more precise conclusion, then probably you will choose big theta. But there are some scenario, like just now I have mentioned, you may have some algorithm. Sometimes you run is constant time. Sometimes that's a best case. Worst case maybe is in linear. You need to take linear times to execute this particular algorithm. In that situation, if you want to just write one sentence, instead of telling people best case is constant, worst case is linear, I just want you to just simply give me one simple statement. Then you find it very difficult. I cannot use the big theta. I probably only can say that, oh, this algorithm, the time complexity of this algorithm is in big O n, because worst case is linear. So it can be better than that. But I'm pretty sure that this particular the time complexity of this algorithm is in OGN. It may be n, it may be better than n. So, and sometimes is in what kind of situation? Sometimes I only know that this algorithm, the best case is linear. It must at least run a linear times to complete this algorithm, the best case. But I have no idea how worse it can be. I have no idea. It's too complicated for me to analyze. In that situation, I only can make a conclusion saying that the time complexity of this algorithm is big omega n. Because I don't know how worse it can be. I only know the best case that it must at least need to run in linear. So it depends how much you know about that algorithm. Then you will choose appropriate notation to represent your conclusion about the time complexity. That's why we will use different notation to represent our time complexity. Okay, so maybe yeah, last 5 minutes. I just trying. Let's say we trying to have trying to analyze this time complexity of this sequential search. Sequential search, in short, just like where you learn the linked list, you just search whether the key A is in the linked list or not. In this situation, you expect that you have two scenarios. It can be it is definitely in the linked list, or A is not in the linked list. So here I first considered my search key A is always in the linked list. Definitely is one of them first. So in that case, I have, you look at this one, it can be the best case. What is the best case? Is the first item. I just need to run in constant time, finish, end. Then in the best case scenario, if I assume that the search key is always in the list, the best case, the time complexity of the best case is big theta 1. And then what is the worst case? That's when you need to, worst case, probably the search key is this one, the last one, the last nodes. That's when you need to run this particular while loop n-1 iteration. Then you can reach the last item. Then you found the key. In that case, the time complexity is C2 times n-1 plus C1. So I can make a conclusion. In the worst case, the time complexity in the worst case scenario, assume that the search key is always in the list, I can conclude that it is a big theta n. It's a linear function. Yeah, like I said, all these constant not so critical. I'm only concerned about this n. And what is the average case? That's mean it can be this one, it can be this one, it can be third one, can be fourth one, can be any. All have equal chance. Theoretically, yeah, I can make this assumption. I think it makes sense. The search key, you give me a search key, it can be the first item, can be second item. If there's no any special reason, I think I can make the assumption that they have an equal probability. Every item in the list has an equal chance, yeah, as a search key. So in that case, I need to consider all the possible case. If it's the first item, the time complexity, the search time I need to take is like C1. If it's a second item, it's C1 plus 1 iteration, C2. If it's the third item, it's C1 plus 2 C2. Yeah, it's C1 plus 3 C2 if it's the fourth item, and so on and so forth. If it's the last item, which is the worst case, which is the C1 plus n-1 C2 times C2. So since I said they have an equal probability, that means I got n item. I got n item in the linked list. So every item have equal chance, that means 1 over n. This is probability for each case. Every case has the same chance. So I can rewrite this series into this summation into this form. Easy to read, maybe. I don't know. 1 over n summation C1 plus C2 I minus 1. I equal to 1 to n. Yeah, so that means I equal, so it's 0, 1, 2, 3, 4, 5, 6 to n minus 1. So what is the summation of this? You have C1, 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 C1. That means you have n C1 plus C2 is 0 plus 1 plus 2 plus 3 plus 4 plus ... to plus the last one is n minus 1, which is a Arimetric series. So this series, what is the summation? I have n term. The first term is 0. The last term is n minus 1. Then C2 plus C1. So this one is n 1 over n. This one is 1 over. Outside there's another 1 over n. I think I have a proper one. So I can rewrite this thing. Then after that you simplify this, then you will find that this one should be C1. Then this part is something n minus 1. So it's C2 over n. C2 over n times... sorry, this one I write wrongly. This one should be n over 2. I got n term, n over 2. Then 0 plus n minus 1. I got n term, n over 2. The formula is n over 2. I got n term, n over 2. Then the first term is 0. The last term is n minus 1. So you simplify it. Okay, in short, after that you simplify all this expression. You can conclude that on average, the time complexity, if I assume, again I need to emphasize, if I assume the search key is always in the list, is big theta n. Okay, so this is the best case is constant, worst case is in big theta n, and then average case is in big theta n also. Yeah, if I assume the search key is in the list, then of course I need to consider what happens if the search key is not in the list, which means you always have to search all the way the whole linked list. Then you conclude that, okay, fail, the key is not inside. Then you will find that you expect you need to run C1 also. Then this one you need to run n iteration, including the last one. You need to check. After that you are left. So it also is a big theta n. If the search key is in the list, then I need to take big theta n. If the search key is not in the list, I also need to take big theta n. So yeah, there are some probability, but both cases, on average, if it's in the list, on average is big theta n. And then if it is not in the list, you always need to take big theta n. So overall, the time complexity of sequential search is big theta n. I can make this conclusion. On average, I should say on average, yeah, it should be in big theta n. Because in the search key, on average, yeah, when I said this one is on average, right? But take note that, so you find that if you find online, they will probably tell you that if you just simply said sequential search, what is the time complexity of the sequential search? What is the time complexity of sequential search? They probably will just tell you that it should be in big O n. What is the difference when you say it's a big theta n and big O n? The reason is because you need to remember that there's a scenario. The best case scenario actually is only, you just need to take one iteration. It's a constant time. The best case scenario. So in that, so you cannot, when you said in general, I mean, I'm talking about this whole algorithm, the sequential search. What is the time complexity of sequential search? I'm not talking about best case, worst case. I'm just asking you this general term. Then you probably, the best representation, you only can set is big O n. But if today I'm talking about on average, what is the average case? Then you can conclude on average, whether it's inside or not inside, on average is big theta n, because always is linear. On average, inside the list, on average is linear. If it's not in the list, whether it's on average or not, it's not in the list, so it's still linear. So overall, this algorithm on average case analysis is big theta n. But if I didn't mention on average this word, then you only can set that it's big O n, because there are some cases which is constant time. So that is how we select the right notation to represent our time complexity. So in today's lecture, I'm cover the big omega and big theta. I think, and notation representation, and how do we use this notation to represent an algorithm, the time complexity of an algorithm. And you will find that a lot of time to analyze all these algorithm, you very easy to encounter some series here and there. And when you do this time complexity, the asymptotic notation, you will find that you sometimes, okay, all these cases are really simple, so you don't need to take the limit, but sometimes you may need to use to taking the limit. Okay, so before I end this, sequential search, the reason why is if you take a linear, you'll find that because if the data is not in order, a lot of time you have no other choice. You have to read through the every nodes and then trying to compare the key. It's a kind of a brute force approach or naive approach. So very other choice, you have to read every element at least once. So the time complexity, is normally this kind of time complexity very likely is O(n). And then you can later just now someone mentioned about the binary search. Later we will talk more about it. Then you will find that how to improve. In the second half, we will cover the hash table. We will show you how to further improve it. So actually, you find that sometimes if you have a better algorithm, you can improve the time complexity a lot from linear to logarithmic. And it's not like what your implementation, you can save 1 line, 2 line. That one is nothing. We normally, when we said improve the algorithm, we really introduce a new algorithm. The improvement should be from one class, from linear class to the logarithmic class. I think I still have a few more slides. I think already 11:30. Okay, before I end the today lecture, next week, because Tuesday is the Chinese New Year, so what I will do, probably today evening, I will give another streaming and then upload it. You can watch that video, or you want to attend in the evening probably around 6:30. I will give another lecture, maybe also complete where I stopped right now, and the stack and cube, from 6:30 to 7:30 to cover the next Tuesday lecture. Okay, that is today's lecture. Maybe I can answer the last question. If Fn growth rate is faster than Gn, if Fn growth rate is faster than Gn, does it mean that if Fn grow faster, that means Fn will take longer times. That means that algorithm, the time complexity, the algorithm, it take longer time, it's slower. You are right. When the problem size increase, important. Faster growth rate implied that the algorithm is not that good. It's very slow one. The time it take longer times to run. You are right. That is important. A lot of time people confuse with that. Yes. Okay. Any other question before I end the streaming? If not, that is today lecture. In the evening, around 6:30, I will give the makeup lecture for next Tuesday due to the Chinese New Year. I will cover the rest. Of the slide here. This will be covered in the evening. Actually, only the last few slides. And plus the stack and cube. Okay. If no other further question, thank you for your attending. Goodbye.